Good morning, student. Welcome back to third session of this series of lectures on statistical thermodynamics. Today I am planning to discuss translational partition function. In my first lecture, I have discussed the fundamental concept of statistical thermodynamics. Now you are aware of this different ensemble, canonical ensembles, difference between the microstate and macrostate. And in my second lecture, I discussed what is actually partition function. And categorically, I had discussed the canonical partition function is a complete system and molecular partition functions. And today I will discuss only one partition function, that is the translational partition function. And particularly you know that molecules of a gas, of course I am talking about the ideal gas, do not have the same energy. And with the help of partition function, most probable distribution of energy is possible, or the number of molecules, how that molecules is distributed among these different energy levels. And it is a universal truth that whether it is a diatomic molecules or polyatomic molecules or monoatomic gases, all possesses translational energy. And so therefore it is very essential to derive the translational partition function. And particularly, of course, molecular evaluation of the translational partition function. Now, as I already discussed with you that you know the partition function, you know the definition of the partition function, and I have also discussed that is one of the very important concept of statistical thermodynamics, and it can be represented as canonical, means capital Z or capital Q. I have already discussed with you. But the molecular partition function can be represented as small z or small q. And definitely, because again I am talking about this, it is nothing but you know that the different energy levels are there, and it is the probability, and it also depends upon the temperature and other things, that how that molecules is distributed. So it provides a quantitative, not qualitative, quantitative measurement. How many quantum states of a molecules are thermally accessible. And that means it is simply significant population at a given temperature. Now, if you understand the formula, it is sum over state, as I told you, summation of maybe I from one state to from I from infinity. So and I can write like that. And if I write, as I told you, that you can write, I did Boltzmann constant T. So this part is important. I have to substitute the value of particular energy. Now, in your course, when I have seen your course content of MSc second semester, course number 203, I have seen that you have to study all the partition function. That means derivation of all the partition functions. And first is generally translational. So today I will discuss translational, then in second lecture I will discuss the rotational, and then I will discuss the vibration, and lastly I will discuss the electronic partition function. And of course the molecular partition functions can often be factorized into components. Whereas if we are talking about the energy, it is the sum. A molecules possess a different energy, so translational energy plus rotational energy plus vibrational energy plus electronic energy. So today's objective is that evaluation of translational partition function, and of course now you can understand that it is a subject that can be acted as a bridge between the quantum mechanics, because whenever I want to use the translational partition function, so I need the value of translational energy, and which can be derived from the quantum mechanics. You all know particle in a box, one-dimensional box or three-dimensional box. So definitely I need the help of quantum mechanics. Okay. Now before going into details of the subjects, now there is a very simple system. क्योंकि आप लोग for the student purpose I have deliberately prepared a common transparency so that you can understand how different partition function can be derived using different energies. So I have written translational energy, rotational energy, vibrational energy, and electronic energy. Of course, whenever we will deal with that electronic partition function, because except for hydrogen atoms, there are no simple formula for the electronic energy. But as you know that, you all know that if you understand that particle in a box, so that the formula of the translational energy is n square h square 8 ml square. I'll explain when I discuss that complete things. What is n? It's a quantum number. What is h? What is m? Mass of the molecule, and L, the length between these two things. Then similarly, today I will not discuss the rotational partition function, but you know that it is we will use the rigid rotator for calculation of the rotational energy, and then for simple harmonic oscillator we can calculate the vibrational energy. So what we will do, again I am saying the same thing, that I have to substitute the value of this energy. So because today I will derive the translational partition function, so I need the values of this translational energy. And when we substitute the translational energy in this equation, partition function equation, and of course summation is very difficult because there are large number of, if I see the translational, they are closely spaced. So that summation can be replaced by the integration. So if I integrate this equation, I will get the value of translational partition function. These are the final equation. I will derive this. It is actually Boltzmann constant Kb subscript and 3/2. So today's objective is that derivation of the translational partition function. In my first lecture, I have discussed that I have used large number of books. But frankly speaking, and I must confess that for the sake of student, for clarity and novelty, the derivation given in the books of thermodynamics for chemists is very simple. Similarly, the derivation given in the books of Atkins physical chemistry are very simple. Because what we are doing, suppose we can consider a monoatomic gas or any diatomic gas, maybe nitrogen or oxygen or hydrogen. And we consider that there is no force of repulsion or attractions. And particular state I can take a rectangular box, and you know that. So maybe x direction, maybe y direction, maybe z directions, and or a particle in one-dimensional box. That is also possible. Particle in one-dimensional box. So, and the distance between these two is, you can write capital L, or even in some books it is capital small l can also be written. And the mass of that particular molecule is m. And quantum number is, of course, translational quantum number may be 1, 2, or 3. So there are two methods. Either we use the one-dimensional box, which is very simple. We'll first derive only one system, or we can derive for different system also, nx like ny, nz. So for the student sec, I'm using this books for derivation, and this Atkins is very simply derived these things. And the final equation, as I told you, that this formula is 2 pi m mass kb t, it is underscore 3 by 2. Volume, LU meter cube, that is the Planck constant. This is actually the final formula of translational partition function. Now, again, as I told you that I am using this same thing, whatever it is, or maybe GI, exponential E of translational divided by kbt. So if I consider a one-dimensional box, there is no problem. But if I consider that there is a three-dimensional box and there is a free movement, so therefore I have to write in place of the general formula is n square h square 8 m l square, the length of these things. And if I consider only one direction, so there is no problem. But if I consider three directions, x direction, y direction, of particular right angle to each other, so then in that case I have to use that nx, ny, and nz, and lx, ly, and lz. So because there are three distance, x in one direction, y direction, and the z directions. Because the translational lines are very closely spaced. Very closely spaced. So therefore, the value of statistical weight factor or degree of degeneracy, G of translation, is equal to 1. And that summation is successive integration, you know that, from 0 to infinite. So therefore, I am using, this part is common, n square is m is the mass. I will show you how you Boltzmann constant and T. So there are three parts, nx, ny, nz, L square x, L square y, Lz. So dear student, it is up to you. You can refer the books of Alberti Daniels, you can refer the books of Levine or G.M. Barrow. But for very simple method, if you refer the Glaston, you will see first they consider in one direction and then they derive the whole system. Okay. So for the sake of the student, I will use the simplest method for the derivation. derivation of translational partition function. First point is that translational, so I can write T is equal to summation, as I told you that for this Z I is equal to 1, closely spaced, exponential minus n square h square, sorry, E translational KBT. Bear in mind that for this simple calculation I am using particle in a one-dimensional box, and I am consider only the distance between those is L. So E translational, as I told my first lecture also, in place of capital E you can write epsilon translation, no problem. So I have to write E translation is equal to n square, as I told you it is a quantum number, the integer quantum. H is a Planck constant, 8 m mass of that molecule, L square. I am here using L, you can use the capital L also, you can use nx also. So I have to substitute, very simple, of course is I0, 1 is equal to infinite. So I have to substitute the values of whole E translational into here. So what I am getting, summation infinite exponential minus n square h square 8 m, very simple derivation. Therefore deliberately I have chosen first day, this is the formula. Okay, last step, that means now because these are closely spaced, so I have to integrate it. So from 0 to infinite. Exponential minus n square h square 8 m L square KB and T, and of course dA. Now you know that there are different forms of integral results is obtained. I can write like that, 0, of course n is greater than 1. So should I write exponential minus n square alpha dn? Why? Because that alpha is equal to, I am just taking h square 8 m L square KBT, just that, you know. Now I am not doing this integration. We can use the Gaussian integration and the result will be, results of this integration will be half under root of pi divided by alpha, the results of this integration. So you have to substitute the value of alpha. Like that, if I want to see these things, again I am just showing you that here I am not using 3-dimensional. I am just using only 1 in place of this. I am using only n square like that. So you see, this is the according to the Gaussian integral. What I have shown you that 0 to infinite. Extension like here I have written here n square and like that. So you will see that this is the result. And here I am using this, you see, n square alpha, and alpha you have seen I have the value, and the example is of course greater than 0. Of course, definitely alpha is greater than 0. So you see, directly you can write these things. That means the results of this integration is half pi divided by alpha. Now you substitute the value of alpha. So now I can remove all these things. So translation is equal to half under root of pi divided by alpha. So I have to substitute the value of alpha. Very simple derivations. So let us substitute here. So half under root of pi divided by this. Alpha means h square 8 m L square kBt. So this, if I just use this 2 here, so it will be 4 divided by 2, so what will get? 2 pi. Isn't clear? Is it clear? 4 divided 2 pi m Boltzmann constant T half L square L divided by h square, so h. So what I am getting? So I am getting Q of translational is equal to 2 pi m kBt half or h into L. Now, what I have told you that I am just considering only one case, L centimeter. But actually, there is a 3-dimensional case. That means maybe x direction, maybe y direction, also L. Suppose this is L. So the total partition function, considering all these directions. So what I should write? This is 2 pi m kBt half for one case, suppose x direction, L Again 2 pi m kBt for y direction and 2 pi m kBt half for z direction. So 2 pi m half, 2 pi m half, 2 pi m half. So what I'll get? I will get 2 pi m kBt half 3 by 2 h cube. L, you all know that L, length breadth, L and L, because we are just considering a rectangular box, so it is B. So what is the final formula? Or you can write like that 2 pi m kb whole 3 by 2 h square. That is also possible. So what is the final formula? That is the 2 pi m kbt 3 by 2 volume and h cube. So let me. So this is the simplest method. You have seen that, or as I told you that you can use that first formula. So you've seen that. But as far as the student is concerned, because you always prefer the easy derivation, which can easily be grasped, you can easily be. So therefore, I am deliberately using this simple formula, and this is our final formula 2 pi m kbt. So what I am getting, this is the final formula. And as I told you that I have taken from, this is from Glaston, very simple. Of course, it's a very old book, but every time you have to, whenever you apply, so you have to use the SI unit, Systematic International Unit, and MKS unit you have to use, because you should use the values of, if I talking about the, because there are Planck constant, 6.62, like 10 to the power minus 34 joule second. And it is 1.38 to 10 to the power minus 23 joule per degree, like that. And volume, of course, in terms of meter cube, you have to. So if you know how to calculate the mass, the molecular weight multiplied by 1.6 into 10 to the minus 28 kilograms, so you can calculate the everything. Then you will get these values of. After this class, I will show you some of the things for hydrogen or for oxygen, for argon, for nitrogen. You can calculate the translational partition function. Now, one thing is very important. If you see the recent question paper of any competitive, national level competitive examination, there is a terminology that is called thermal de Broglie wavelength. Thermal de Broglie wavelength. You all know about this de Broglie You all know this thermal de Broglie wavelength. Why I am talking about the thermal de Broglie wavelength, I will explain these things. Suppose, and I'll say what is the actual, how you define the de Broglie, thermal de Broglie wavelength. It is like that. Also, and it is denoted as like that. Anyway, why I am mention this thermal de Broglie wavelength, and it is also given in some books of the Atkins and other things. Suppose in any university examination or any competitive examination or in multiple choice question, there is a possibility to ask question, the calculation of translational partition function, calculation of rotational partition function, calculation of the vibrational partition function. And if I just give you one homework question that calculate the translational partition function of hydrogen molecule at 298 degree centigrade, and so if this hydrogen gas is confined in 1 liter, because volume is very important. So in order to solve that equation, you have to substitute the values of pi, m, mass, Boltzmann constant, Planck constant, and you know that values, it is very difficult to solve these things. But suppose a second type of question, that your examiner will give you that the values of thermal de Broglie wavelength, and temperature. So you have to calculate the translational partition function. So that means there is a relationship between the thermal de Broglie wavelength and translational partition function. Because if you see the formula of that thermal de Broglie wavelength, it is like h 2 pi kBt half, and if I consider it is this formula, and if I just see, so it is thrice, that means it is like that. So what I can write that Q translational is equal to V divided by this. So if I know the value of thermal de Broglie wavelength, I can calculate the translational partition function. I will give you one example, then I will stop my lecture. This is the last part of the translational partition function. Okay, now we know the formula, or now how do you define the thermal de Broglie wavelength? I will not derive, because there is a derivation. This is not in your course. You have to only know that what is actually thermal de Broglie wavelength, or you can write like that, as I told you. You can write like that, h divided by 2 pi m kBt half, isn't it? Same thing. Okay. And our translational partition function, 2 pi m kBt 3 by 2 hq. So what is the thermal de Broglie wavelength? Indicates the quantum mechanical wavelength. Because normal, what is de Broglie wavelength? You know, this is not. But it is different. This is thermal de Broglie wavelength indicates the quantum mechanical wavelength associated with a particle's thermal motion. It gives the wave-like behavior of particle at a given temperature. And why I am using this thing? Because there is a close relationship between this thermal de Broglie wavelength and translational partition function. आपको दिख रहा है ना? अगर मैं इसको 3 बार करूँगा, that means this this, so I will get same thing. So it is like that, V divided by, because cube. So you see, the translational partition function quantifies the number of accessible quantum state for a particular of the translational motion. If you see my first point of this lecture, what is actually that translational part? Number of accessible quantum state. Number of accessible quantum state. Energy levels, and so if I am getting 10 to the power 26 or 10 to the power 30, that means 10 to the power 30 quantum states are accessible at a particular temperature. So, hey. And another color. So what I am getting? Simply translational partition function is volume I must know, divided by I must know the de Broglie wavelength. So आपको क्या मैं समझाना चाह रहा था कि ट्रांसलेशनल पार्टीशन फंक्शन तो आप कैलकुलेट कर सकते हैं, लेकिन अगर आपका ऐसा क्वेश्चन आ गया कि जिसमें एग्जामिनर ने आपको दिया द वैल्यूज ऑफ थर्मल डी ब्रोगली वेवलेंथ, तो आपको कुछ नहीं करना है, आपको वॉल्यूम, मान लो वॉल्यूम 1 लीटर 1 इंटू 10⁻³ मीटर क्यूब, एंड इट इज सपोज 1 इंटू 10⁻10 picometer or like that. So what you will get, the values of, I am just giving one example, अभी मैं exact value आपको बताऊंगा. So you will get the values of translational partition function, and it may be 10 to the power 26, maybe 10 to the power 30. That means these quantum state accessible for a particle. Again, it is a question of the probability, how that different types of molecules is distributed among the different energy levels. Most probable distribution, same thing. Now the last I am giving one, there are many examples because it is a general lecture. So I will give the homework to the MSc students that you should refer some of the good books and at least solve in order to understand the subject. अगर आप सब्जेक्ट को अच्छे से समझना चाहते हैं, फिजिकल केमिस्ट्री थ्रू प्रॉब्लम्स, क्योंकि फिजिकल केमिस्ट्री को अगर समझना है, अगर आप घर में जाके न्यूमेरिकल प्रॉब्लम्स करेंगे तो आपको समझ में आ जाएगा. जैसा मैंने हम यहाँ पे दिस यू कैन कैलकुलेट द ट्रांसलेशनल पार्टीशन फंक्शन फॉर monoatomic gas. Of course, there are ideal gas, there is no interaction between this. Yeah, any diatomic gas or any polyatomic gas. So you must know the temperature because that is important. You must know the Boltzmann constant. Joule per degree. You must know the 6.62, 34 joule second, like that. And mass, you have to calculate the mass of that, whether it is oxygen. So the mass is around 5.3 into 10 to the power 23 gram. For organ, mass is 6.64. You know these things. You know the atomic mass unit multiplied by the 1.67 into minus 28. So you can get it. And then if this is confined in 1 liter in some cases, so 10 to the power minus 3 meter cube. Or directly you can write the values of this de Broglie, thermal de Broglie wavelengths. That can be calculated by this method also, H. And I कई बार आपको बताया 2 pi m kBT half. So thank you very much. Let me summarize the topic. Today I discuss in fact I derived the translational partition function, and I have used the simplest method considering a molecules of a monoatomic or diatomic or polyatomic gases confined in one-dimensional box where the length is L centimeter and mass is m. Then I first derive for one direction, then I use this formula for x direction, y direction and z direction. I will get a complete picture of translational partition. It is a dimensionless quantity. Then I also try to correlate translational partition function with thermal de Broglie wavelength for calculation purpose. And ultimately, if you see very carefully, that the translational partition function increases with the length of the box and of course the mass of the particles. I am taking this observation from the books of Atkins, physical chemistry. And of course, partition function increases with increasing the temperature. And you have already, if you heard my first lecture and the second lecture, I have already discussed the probability of that things, most probable distribution energy levels among the different types of molecules. So friends, student, I think you you have enjoyed this simple lecture of translational partition function. That is the lecture number 3rd. And in lecture number 4, that it will continue for rotational partition function. And once you understand the translational partition function, so you can very easily calculate the rotational partition function also. So again I am going to this thing. Today I have finished these things. In next lecture I will discuss the rotational partition function. So I will do nothing. I will take the values of rotational energy and substitute in our general formula. I will get of course, it is we have to consider the symmetry and other thing, moment of energy. I will explain these things. Then similarly, in 5th lecture, I will discuss the vibrational partition function and electronic partition function jointly. I will use the vibrational energy. Thank you very much.